Hello, welcome back to the Calculus video tutorial series for Mr. Billingham's AP/BC Calculus class. Today we're going to do something you can completely skip if you want. This is from 11.2. For some reason they start off with a review of vectors, but you've almost certainly had that in your pre-cal or pre-cal equivalent class. So you can look at this if you want, or you can skip it. Just to entice you, I will say there'll be a meme at the end. Anyway, here we go. So the text does start in 11.2 with a review of properties of vectors. You should have studied all of these in the past, and you really don't know the details for most vector calculus problems, but a quick review won't hurt. So vectors are things that have both a magnitude and a direction. You probably remember from physics that speed is a scalar quantity. Velocity, on the other hand, is a vector. You have both a direction and a magnitude. Vectors have heads and tails. So the vector with head 1, 2 and tail 4, -3 is the vector that goes from the initial point, or the tail, 4, -3, and ends up at the starting point, or the final point, or the head at 1, 2. And you can subtract the head minus the tail to get an equivalent located vector, which is a vector starting at the origin. So if we do that, we get the following. If I did my work very neatly, you would see that these two vectors are parallel and have the same length. And you'll notice in the second way I've represented the vector as a located vector, I have put left and right less than and greater than signs to indicate that is a vector. So these two vectors are equivalent. The text calls these things arrows. I'm old school. I still call them vectors. This illustration should reinforce the difference between the coordinate point AB and the vector which goes from the origin to the point AB, which is denoted left less than A, comma B, right greater than. We can define a two-dimensional vector as follows. So a two-dimensional vector V is an ordered pair of real numbers denoted in component form as, I don't know what to call that symbol, less than, A, B, greater than. The numbers A and B are the components of the vector, and the standard representation of the vector is an arrow from the origin to the point AB. To find the magnitude or absolute value of V, denoted by absolute value of V, it is the length of the arrow, or the length of the vector, and the direction of V is the direction angle in which it's pointing. The vector 0, 0, the 0 vector, has 0 length and no direction. To find the magnitude, which is the length or the absolute value of the vector AB, which of course is the vector which goes from the origin to the point AB, you just take the positive root of square root of a squared plus b squared. So if the vector was 3, 4, magnitude would be 5. The direction angle of a non-zero vector is the smallest non-negative angle formed with the positive x-axis as the initial ray, and the standard representation of V is the terminal ray. So I think that's all pretty clear. You should have seen it before. It should be pretty straightforward. If you're given the initial point, also known as the tail, and the terminal point, also known as the head, of a vector, you can convert it to a located vector using the following. If an arrow has an initial point or tail of x1, y1 and a terminal point or head of x2, y2, it represents the located vector x2 minus x1, comma, y2 minus y1. And here's a quick example to put our knowledge to use. So I'm going to start off by getting the magnitude. That's absolutely easy. So the magnitude is 2. To help us get a sense of the direction angle, I'm going to go ahead and draw a picture. Clearly, we're looking for a second quadrant angle, and those numbers -1 and √3 should, to help, I can get the reference angle by taking inverse tan of √3 with a calculator, or from memory. You should probably know that the reference angle is 60 degrees. So this angle here is 60, so our answer is 120 degrees. Or for purists, 2 pi over 3 radians. Now let's do one kind of backwards. From the angle and from the magnitude, let's calculate the components. From working with general circle trigonometry, you probably remember that x over r is cos theta, or x is r cos theta. Similarly, y is r sine theta. We'll use 40 degrees for theta, and for r, we'll use the magnitude 3. So the vector has 3 cos 40, 3 sine 40 components. And if we put that into our calculator, we get the components of this vector are about 2.298, 1.928. And then here are the rules for vector addition and scalar multiplication. Look over them as I read them to you. So let u, u1, u2, and v, v1, v2 be two vectors located. Let k be any real number, which is a scalar. The sum, or the resultant of the vectors u and v, is just their new vector, which has u1 plus v1, comma, u2 plus v2. So you add the x components, add the y components. The product of the scalar k and the vector u is just ku1, ku2. You just multiply the scalar by the x and y component. And the opposite of a vector, or negative v, is just the scalar negative 1 times v. It just changes the sign of each of the components. And we can define vector subtraction as u minus v is the same as u plus the opposite of v. If I take any vector v and divide it by its magnitude, I get a unit vector, which is a vector in the same direction as the original vector, but having a length or magnitude of 1. Here's a quick example. So I converted the vector u, negative 3, 4, into the corresponding unit vector, which is the same direction angle, but only has a length of 1, by dividing by the magnitude 5. Also, I can graphically represent the addition of two vectors using a head-to-tail diagram, or what's called a parallelogram diagram. So to graphically represent the sum of the vectors u and v, you can just add the two together in what's called head-to-tail position. The head of u and meets up with the tail of v, and the head of v is the vector sum. Or you can construct a parallelogram with two sides of u and v, and the diagonal is the sum u plus v. The product k times u of the scalar k and the vector u can be represented by either a stretch or a shrink of u by a factor of k, if k is positive. If k is negative, then it'll point in the opposite direction. Take a look at this example. So the blue vector is u, and we have 2u, which stretches it by a factor of 2, 1/2 u, which shrinks it, and negative 2u, which stretches and flips in the opposite direction. Let's work another example. So for a, first I multiply negative 1, 3 by the scalar 2, getting negative 2, 6, and 4, 7 by the scalar 3, getting 12, 21. Then I just add the components to get 10, 27. And as defined, vector subtraction is the addition of the opposite, so I've added the original vector u plus the negative 1 times v, which is negative 4, negative 7, getting negative 4, negative 5, negative 4. And getting the magnitude of 1/2 u is pretty simple. First I multiply it by the scalar 1/2, getting negative 1/2, 3/2, and then to take the magnitude, I just take the square root of the x component squared plus the y component squared, and I wind up with root 10 over 2. We'll complete the section by looking at an example involving ground speed and air and wind speed, and do the following example. This is a good pre-cal kind of problem with vectors. So Boeing 727 flying due east at 500 miles in still air, which would mean also 500 miles per hour relative to the ground, suddenly encounters a 70 mile per hour tailwind acting in the direction 60 degrees north of east. The airplane holds its compass heading due east, but because of the wind, it has a new ground speed and direction. What are they? So let's represent this with a diagram. So the blue vector u is the wind, which is a little bit of a tailwind, but also off to the side. It's 70 miles per hour at 60 degrees relative to the x-axis. If I put both of the vectors into component form, we can just add them and get the vector u plus v. So the vector u plus v would be 535 root 3. And the easy way to get the magnitude is, of course, to square 535, square 35 root 3, add the 2, and take the square root. So the plane is now flying 538.4 miles per hour relative to the ground at an angle 6.5 degrees north of due east. Anyway, that is the end of this presentation. And here is your meme for being so patient and waiting. Have you ever seen the two of us in one place together? Anyway, thank you for watching. This concludes the first part. The second part of 11.2 is the calculus-y part. That's the part you really ought to watch. I'm going to go and work on that right now and get that out to you as soon as I can. Hope you're all staying well, and I'll set up a video tutorial, a chat session through Teams for Friday in case anyone wants to check in and say hi. All right, and if you get AP questions ready for me, I'll be glad to answer those at that time.